That should be clear in the question statement. Let's just read the question. 2.6 you said, right? So 2.6 says from problem 2.6 or for problems 2.6 and 2.7, calculate the uniform load in addition to the beam weight. So the beam weight needs to be added. It says in addition to the beam weight.
So is that load all combined, or are they like, does that make sense?
What's the question?
The weight of the beam.
You need to consider weight of the beam and a uniform load, yes.
So when we find the moment of cracking, that P, is that included in the weight of the concrete?
Of course not P, the distributed. P usually we use for concentrated load. But in this case, the distributed load would include both the beam weight as well as the additional weight. So let's say the beam weight let's say is 1 unit, and then you need to have additional load Q, where together generate the amount of moment that you need. Any other questions? Okay. So problem 2.6, the geometry is given obviously. So, and it just say the unit weight that you want to consider is 150 pounds per cubic foot. So you can easily calculate. And this 150 pounds per cubic foot, as you can see, says reinforced concrete weight. That means consideration of the concrete as well as the reinforcement. Any questions on 2.3? So 2.3 is a T section. What we solved in the class was a rectangular section. What you are solving is a T section. Okay, so if no questions, let's continue where we left off. Please initialize in front of your name. So what we are looking at is at this time is cracked sections. (3.2) cracked sections. So one thing we discussed last time is when you are looking at the cracked sections, we consider material properties are linear. So that is meant to make the use of moment of inertia consistent with the concept of geometric characteristic of a section for a material that is linear. So when you use moment of inertia, the underlying assumption is that you have one type of material and it's linear, both of them, one type and linear. Could you please put aside your cell phone? So when we are talking about one type of material and linear, this is in the context of moment of inertia. Otherwise, the moment of inertia is not an applicable term. Furthermore, when we talk about linear properties, it has some other application, such as the one we discussed last time. That is, if you consider stress-strain relationship for concrete. When you consider stress-strain relationship for concrete, obviously again this characteristic is not linear. What we said was, if you want to apply what we cover under this section, it's only applicable until the point that is approximately linear. Up to that point you can apply the method, and below that you cannot apply. Obviously if you apply as you go higher up, and if you apply, you have more and more error. If you are slightly above, you have a slight error. If you have a lot above, you have a lot of error. So the general idea is you just limit up to the point that is approximately linear. This is, again, one thing is in the context of this concept. One thing is parallel to that in the context of damage. So if you apply stress beyond the linear range, you will have permanent strain. That strain would not go away. That strain is such that it would represent permanent damage in the system. And the general idea is it would be a good approach to limit the amount of stress in concrete up to the point that concrete is almost linear. That's a good approach. Why? Because when you apply the loads every day, you load, unload, you don't keep adding damage to the system. We don't say that the section cannot take more moment. The section can take significantly more moment, and the stress can go significantly higher under exceptional conditions. Let's say, again, there is an earthquake someday. That's okay. The structure would move and get would be damaged to some extent. What we are talking about here is under service condition. So when you have everyday loading, you don't want to stress the concrete beyond approximate linear range. This linear range is not a perfect number, in the neighborhood of 0.5 F prime C. A little bit more, a little bit less, depending on who is looking at the problem and what criteria they are imposing. If you look at some books, they say 0.4, 0.45, 0.5, or even slightly larger. But in the neighborhood of 1/2 of F prime C. Why again do we impose this limit? In order to limit damage to concrete in compression. It's very specific. We want to limit damage to concrete in compression as a result of everyday loading. Therefore, what we want to do, we want to relate M service to stress in concrete and rebars. In general, we wanted to relate moments to stresses. In this case, we become a little bit more specific. That is, we are specifically talking about M service. M service, that means again limiting the stress below some level, as well as maintaining linear properties to be able to apply this method. There are two things in parallel, almost independent. One, if you want to use I, your material properties need to be linear. That's one domain. Another domain is if you don't want to impose damage to concrete in compression, don't go beyond the linear limit. So they go together, and as a result, this is what we are talking about. Any questions so far? Okay. So what do you think we should impose in terms of stress limit on rebars? This was a stress limit on concrete in compression. What is the stress limit on rebars? Any suggestions?
Would be, or it's going to be different because of the stress strain graph of steel.
So what limit would you, can you propose any numbers, any?
Just nothing in terms of numbers.
Okay, any limit that you want to impose on rebars?
The amount of stress at which we have strain at 0.5 FMC.
In rebars.
Yeah.
Rebars are in tension, concrete is in compression. How are you relating them? What we said is we don't want concrete in compression to have compressive stress more than about 1/2 of FMC. The second question is, what should we do for rebars in tension?
Don't want your rebar to surpass 60 KSI in stress.
Which is the yield stress. So that would be one starting point. We will modify it, but that's a good starting point to think about. This is stress-strain relationship for rebars. The suggestion is that limit it up to here, which makes sense. One, up to that point, steel is linear. It satisfies the requirement we wanted. From a damage point of view, if you pull the rebars up to the yield stress, let it go, there is no permanent strain. So it satisfies both requirements. That's a good limit to start with. So far we have talked about concrete in compression, rebar in tension. Let's now talk a little bit about concrete in tension. Concrete at this time is obviously cracked, correct? We say cracked section. By definition, we say the strain and the stress in the rebar, in the concrete, is beyond its tensile strength, and as a result, concrete is cracked. One thing we would like to talk about concrete in tension is that we don't want for the crack to be wide open. We want to be able to control the crack size. Why? One reason is if the crack is wide open, people can see it and could be afraid of a cracked structure. So what's a good crack? A good crack is the one that cannot be seen. Okay? Of course, when I say seen with the naked eye, if you look at the reinforced concrete structure closely, pick a magnifying glass and know where it would crack. Look up closely, you will see the cracks. But that's not what people usually do. So from a usage point of view, a good crack is the one that cannot be seen. From a material properties and durability point of view, the wider the crack, the more likelihood of the rebars to be corroded due to the fact that materials can go into the crack and gradually lead to the corrosion of the rebars. So in general, we want to control the size of the crack. We don't want for the crack to be wide open. Historically and experimentally, people have seen that a good way to control the crack size is to limit the stress in the rebars. So that's an indirect approach. It says, I want to control the crack's size. What's the best thing to do? Based on experimental results and other studies, a good approach is don't let stress in rebars to go too high. You remember, we said you have a reinforced concrete section, and when it's this case I'm showing a negative moment. As long as it's not cracked, the section is not cracked, the stress in rebars is not high. When the section is cracked, the only thing holding the two sides together is the rebar. The larger the strains in the rebar, the wider the crack. In fact, people who are more experienced with concrete, based on the size of the crack, can give you a best estimate of what's the stress in the rebars. The wider the crack, the larger the stress in the rebars. Again, based on past experiences and experiments, approximately, if you limit the stress in the rebars to 1/2 of f prime Fy, you would be able to control the crack size to the reasonable opening. This 1/2 of Fy obviously is less than Fy, which is a good thing. We said we don't want to go over Fy, we still don't go, we make it smaller. To summarize, if we limit the concrete compressive stress to about 1/2 of F prime C, we will expect a good behavior from concrete in compression. And if we limit the stress in rebars to approximately 1/2 of Fy, not only do we have rebar that is linear and as a result of unloading would not have any damages, but also we control the crack size to a reasonable opening. Two constraints. What are those two constraints? The constraints are when you are looking at service condition. We are not saying a reinforced concrete section should not have a stress in concrete more than 1/2 of F prime C or in rebar more than 1/2 of Fy. That's not what we are saying. We say under service condition, that's what we say as a limit, not under exceptional cases or extreme loading conditions. We said we want to relate moment to a stress. It could be you have been given for a specific section a moment, and the question could be find the stress in rebar and concrete. It could be alternatively the stress limits in concrete and rebars are given, find the moment that would not generate stress more than the limited values. What does that mean? For instance, you have a bridge. Let's say there is an old bridge, there is no document on that bridge, and the DOT wants to know what is the heaviest truck they should allow to pass over this bridge on a daily basis. Okay, that should be a problem you would be able to solve by the end of this lecture. A practical problem. There is a bridge, and then we say, what's the heaviest truck we can let it pass over a bridge? What you would do if that was the case, you would need to know what's the cross section of the bridge and what the rebars are. Then you would say, what is the maximum moment I can apply to that section such that two things would happen. One, stress in the rebars here or in concrete there is approximately less than 1/2 of F prime C. And two, the stress in the rebars is approximately less than 1/2 of Fy. Is that the heaviest truck that should pass over the bridge? No. That's the truck that can pass over the bridge on a daily basis. A question could be, what is the absolute heaviest truck that can pass over? That's a different question. We can answer that later. Okay, at this time we say, what is that, what's the amount of load you can apply to that structure every day? That could be equally applied to a floor system. That means, let's say that this floor is made of reinforced concrete and someone wants to change the use of this building. This is a classroom. They want to make it a computer lab. Okay? You need to compare amount of load that's going to be applied every day and does it satisfy this requirement that you have. Let's say someone says, I want to use this as a library and put lots of bookshelves here. You can evaluate it and see, would it be on a daily basis reasonable to do so. Okay? So, relating moment to a stress, is what we study in the domain of section analysis. You can be given this to find this, you can be given this to find this. It doesn't matter which way you go, there is only a relationship between the two, and that's what we want to discuss today. For now, we look at rectangular sections. This is, let's say, a section, and this is the rebars. And our question is, how do we go about relating stress to moment? What types of relationships can we develop to relate those two together? Okay. What should we do? What is our question? How do we relate moment to a stress? Transform the section. Okay, let's say we transform the section. And then what do we do?
Determine charges.
And then
Then we can find moment inertia.
find moment of inertia.
Then you can use equilibrium things.
Last part.
Then you can use like the stress on the scale of concrete to determine moment.
I need a little bit more complete statement.
Yeah, then we can use the equation sigma is equal to my over I.
Sigma equal my over I, and then we solve the problem. That's certainly one way of doing it. That's an effective way of doing it. We will talk about that in a moment. That's not the simplest way of doing it, however. We want to talk about a simpler approach. We start with a simpler approach, and then we get to this point that is based on section analysis and use of the moment of inertia. So let me start with an approach that is specific to rectangular section. This is even better than what I will describe in terms of a general approach. This is a general approach. What I want to talk about is a simpler approach, but applied only to rectangular sections. So if you have a rectangular section and you want to analyze that section without the use of the transform section yet, moment is equal to force times arm. We need to know how much force we have in rebars in tension and how much force we have in concrete in compression. When we apply M service here to this section, when we apply a moment, rebars will go to tension and concrete at the top goes to compression. As a result of this moment, this compression and tensile force will develop. These are resulting forces. What does it mean, resulting forces? As a result of moment, stress within the compressive zone is not constant, because the strain within the section is varying linearly and the neutral axis is somewhere. Within the compressive zone, concrete is in compression, but not under constant compression. The compressive stress varies over the depth of the section. The rebar is under tension. What we know is, I guess I erased it, linear stress strain relationships. So you apply the moment to the section as we discussed before. If this is the section, and you apply the moment, the top part goes to compression, the bottom part goes to tension. They generate this coupling force that would resist the moment. The arm between these two forces, this is the arm. This force times this arm, or this force times this arm, is exactly equal to the moment. That's the way the section resists the moment. That's why, as we discussed before, we put rebars as low as possible. If we put rebars halfway up, then the arm would be smaller, you need much more rebars. So we want to have rebars and concrete as far apart as possible to increase the arm so that the moment could resist the external moment. What we want to understand a little bit better is, in terms of the tensile force, obviously the force is at the location of the rebar. The question is, where is the compressive force?
It's at 2/3 of the length above the Newton axis.
2/3 from here to 2/3. If this is x,
Yeah, 2/3.
and why is that?
Because it's at the centroid of, like, distributed.
You are looking at this one.
Yeah,
What is this?
this is the strain.
Okay, what are we talking about?
Yeah, but the stress is the strain times.
That's correct, because of this.
Yeah.
So you are right in that. If you go from this, the strain variation within the section is linear. Why? Why is this the case? We talked about it 2 lectures ago. Based on beam theory. Based on beam theory that we are using, which is Bernoulli's beam theory, the strain variation within the depths of section is linear. We want to go now from strain to stress. A stress variation within the section now is also linear. Why? Because material properties is linear. These two linear curves have very different reasons. This has to do with our beam theory that we are applying. This one has to do with the fact that we assume material properties will remain linear. Now, you said the resulting force will be at 2/3 from the base. What are you thinking about?
The centroid of the stress distribution.
Why should we look at the centroid of that stress?
Because it's equivalent to the distributed load on the compressive part of the concrete.
Is that a line, the stress applied to the area that what we are considering the cross section? Is the cross section in the compressive zone a line?
What do you mean by line?
So what you see here is the variation of stress within the depths of section. This is compressive stress. Okay? So here we see a variation over depth. The concrete in reality has some width. So what we have if you want to visualize the state of stress in concrete in compression. If you want to look at it 2D, is that triangle or that triangle at the top that you could see. If you think about 3D, what is the state of stress on concrete? How does it look like? The state of stress would look like this. I'll try to show a 3D drawing here. If you think about this blue as your cross section and think about the compressive zone, the compressive zone is under a state of stress that has this geometry. So if you look at it from sideways, this is what you see. If you visualize it in 3D, this is the state of stress. Given that the stress across the width of the section is constant, is not changing, and the reason is not changing, we said strain does not change over a line. As a result, what you said is correct in that in order to find what you need to find the centroid of this shape. Why? Because force is a stress times area in general if a stress is constant. In this case, stress is not constant. Therefore, force is equal to the integral of stress times incremental area of the compressive zone. So this is over compressive zone. So when you want to go from stress to force, you need to work with area. You cannot work with lines. A stress multiplied by infinitesimally small area integrated over the area gives you the force. So this is the general form that you need to consider. Given, however, the fact that the stress across the width of the section is constant, we can simply say we just think about this triangle, and if we find the centroid of this triangle, that centroid is at the same elevation as the centroid of the resulting force. So that means this distance and this distance are the same. So where is the resulting compressive force? In order to find the resulting compressive force, the only way mathematically you can do it is you integrate stress over the area. But as we just discussed, the result of this integral and looking at this triangle is the same in terms of the location of the resulting force. Therefore, as you said, the compressive force will be applied at 2/3 of the height. Please do not think that compressive force always is applied at 2/3 of the height. That is not the case. In this case, having all the assumptions that we had, primarily the fact that concrete and steel remain linear, Otherwise, in general, it is not at 2/3 of the height. We look at other cases later on, maybe today or tomorrow. If material properties is linear, if we use this, which we do, then the resulting force is at 2/3 of x from the neutral axis. So don't forget the constraint. It's not general. For this case, that's the condition that we have. So we found the location of the compressive force as a function of x. Now the question that still we need to answer is, the arm is now understood. How about the force? What's the force, or compressive force or tensile force? How much force do we have? How do we calculate the force? First, what's the relationship between the compressive force and tensile force? They should be, as you can see, they are opposite and they should be equal. Why should they be equal?
They make a force coupling.
Okay, but why, as a result of that, why should they be equal?
Else the beam wouldn't be equal.
Otherwise, you don't have equilibrium. Sum of the forces in the horizontal direction has to be 0. Sum of the forces in the vertical direction needs to be 0. Sum of the moments need to be 0. The fact that sum of the forces in the horizontal direction is 0, the value of C and T should be equal. So using equilibrium equations, or equation using equilibrium equation, which is the sum of the forces equal to 0, we consider C is equal T in terms of absolute values. Of course, the direction is opposite, but the value of C is equal to the value of T. T is equal AS FS. What is C? How do we calculate C?
ACFC?
Is a stress in concrete constant? Is not. The stress is not constant, as we see stress changing. If the stress was constant, the stress times area would give you the force. Now that it's not constant, what's the answer?
You have to integrate the stress over the area.
You need to integrate the same way that we discussed in the terms of the centroid. You need to integrate the stress over the area. And if you integrate, what would be the outcome?
We would get a uniformly distributed load.
Of course, not uniformly distributed load. When I say uniformly distributed load, you are using three terms: uniformly distributed load. Let's not think about load. Instead of load, what should we say? Stress. So we are talking about section analysis. There is no load. We are talking about stress within the section. Uniformly, there is no uniform because it's varying. Okay, therefore, what's the maybe a specific description of that state of stress? Linearly varying stress within the compressive zone. If you have linearly varying stress within the compressive zone, what is the integral of stress times dA? What is that integral? You wanted to say something?
For the area, would that be B times X
B times X is the total area.
or the compressive zone?
That's the area. How do we change it to force?
Well, applying the equation force time equals, stress equals force over area.
And the stress is not constant in this case, varying linearly. Because it's varying linearly, if you integrate it, you would see, perhaps you have seen that before, is going to be 1/2 of Fc times B times X. So this is the average stress for a linear variation. This is the area. So the compressive force is 1/2 of FCBX. B is how wide the section is, X is how deep the section is. 1/2 because the stress is varying linearly. What is FC? Stress in concrete where?
At the limit point for,
At the top highest section point of the section, maximum stress. That FC is here. Maximum compressive stress. So if you consider maximum compressive stress and linear variation of stress within the depths of the section, this is your compressive force.
But the location of
The location is not at mid-height. The force is 1/2. The location is at 2/3 from the neutral axis. We took care of the R. We took care of the force. Now we can calculate the moment. So moment, M service. Which one of these two should we use? This one or this one? The answer is either one. They are equal. You can use the C as a compressive force, you can use the T as the tensile force. If you calculate them through the correct procedure, you would get the same value. Therefore, this is equal to T times R or C times R. Given that C and T are equal, the amount of moment is simply tensile force times R or compressive force times R. If you use tensile force times R, you find a relationship between rebar stress and the moment. If you use compression times R, you find a relationship between concreting compression and the moment. And those are the things we were looking for. What was the relationship between moment and stress in concrete, or between moment and stress in the rebars? And that's where we arrived at. So, M service is equal to T which is AS times FS times the arm. The arm is D minus X divided by 3. Is that what we were looking for? You see a relationship between the service moment and a stress in the rebar. Is everything else known? Like, do we know the value of X?
Section analysis.
With section analysis, you find the centroid of the section, you find X, or with that simple relationship you have for K. We know how K is related to N and rho. You use that relationship, find K, from K you find X, you plug in here, you have a relationship between M and Fs. If M is given to you, you find Fs. If Fs is given to you, you find moment. X is equal to K times D. We also know K is root of N rho squared plus 2N rho minus N rho. This we know from before. So if a section is given to you and you have this question, I have so much moment, what is the stress in the rebar? What you do is first you find the location of the neutral axis or centroid of the section. For a rectangular section, you could easily use this relationship. You find K, you multiply X, you find X by multiplying K by D. Or if you plug that in directly, M service is equal to AS Fs times D minus KD divided by 3. If we factor out D is equal to AS Fs D times 1 minus K divided by 3. We define, historically people have defined a different parameter J, which is equal to 1 minus K divided by 3. Therefore, finally, M service is equal to AS Fs J times D. This is what we were looking for. What are the components here? AS Fs is the force. What type of force? In this case, the tensile force. What is JD? JD is the R between the tensile and compressive forces. The reason these terms are defined, you can see a parallel here. Both X and J are or arm related to D. K times D gives you the depth of the compressive zone. K times D gives you the depth of the compressive zone. J times D gives you the arm. Those are two change of variables or parameters we often use. You can see in concrete books that they are used. I'll finalize our discussion here with this statement when we take a 5-minute break. Let's say you want to limit the stress in a section to 1/2 of Fy. Going back to that bridge case, you have a bridge, you have a cross section, you want to know what's the maximum load that could be applied to the bridge. You look at the cross section, you say if I want to limit Fs to 1/2 of Fy, I replace this with 1/2 of Fy, multiplied by As, get the force, multiplied by Jd, get the moment. That's the moment. Where do I get J from? J is 1 minus K over 3. Where do I get K from? K is this. You calculate K, you calculate J, you find this relationship, you find the M service. If you have M service, given the load applied, you say, don't let a truck more than 25 kips pass this bridge. So that's practical application when you want to rate a bridge. What is the, or any floor or any element for that matter. So we'll take a 5-minute break, then we talk about how to relate moment to stress in concrete, and then we look at examples.
I've never worked with dead loads before. So when I was doing homework on 2.6, I stopped there because I didn't know. Okay, so I solved for the distributed load. That's what the question is, right?
I usually don't look at the student's solution answer. You can just ask me your question.
So how do I solve for the distributed load of the concrete beam given the weight? So if I'm given 150 pounds per feet cubed,
Okay.
I'm given a cross section of
Some cross section,
Yeah.
B and H.
P and H,
Okay.
and then I'm given the length, which is L.
So how do you calculate the weight of that beam?
The distributed weight.
How do you do that, do you think?
Do I just multiply by this volume?
And if you multiply by volume, what do you get?
I just get pound weight.
That's the total weight.
Yeah, but I don't get the distributed weight.
And if I tell you I have 100
So you're
pounds,
saying if I just times by this area, I'll get per feet, and then
That's
times 28. Okay. And then what I just minus, so if I once I find M crack, that was my goal. That was just easy because I just used I of G, right?
sure.
So
Of course, for 2.3, you need to IUT as well, but
I did
that's
2.3. I
2.3.
did both, yeah.
Okay.
M crack, I know that
You can find the
because it's simple,
distribute.
right? It's just P. Because it's just everything's even.
Of course, P, usually we use it for concentrated
Yeah, it'll
load.
be PL over 4.
So that is concentrated load, not distributed
Because
load.
this shear load equals just one load in the middle.
That's a different statement.
Well, that's for the reaction
Yeah.
forces. Okay, I have to think maybe a little bit more in my moment.
Yes, yes.
But
That's the
whatever-
statics.
Whatever this is,
So you can find the load that would cause the moment
so basically solve for a moment.
and then solve for the load that gives you this moment.
Yes,
And then that load is sum of two loads.
yes. And
You have
minus
one,
this.
you find the other one.
Am I minusing this to find the
Correct.
moment? Okay. Because we haven't worked it with.
That's the objective of homework.
Okay.
It's okay. After that, it's like, I
Do we have the sign-up sheet somewhere? Thank you. Everyone signed up? You didn't sign up, or someone at the back? Could you send it back? Okay, let's continue our discussion here. Before I erase some of this stuff, any questions on what you see on the board? Okay, if no questions, what we discussed last time when you're analyzing a section under service condition, that means a cracked section, you can find a centroid for a rectangular section using this equation. And then what we discussed today was how to relate moment to stress. Relating moment to a stress means section analysis. Instead of saying relate moment to a stress, I say, can you analyze this section? Can you analyze this section means can you relate internal forces to stresses? What we did today was analyze a cracked section. What we did 2 lectures ago, we analyzed an uncracked section. What we did today was based on the fact that moment is force times arm. In order to calculate the moment, we needed to calculate force and arm. We talked about those one at a time. The variation of strain within the section is linear because we use Bernoulli's beam theory. The variation of, I'll put here strain, this is incorrect. Please correct this. This is a stress, not a strain. The variation of stress within the section is linear because material properties is linear. So given that the stress variation within the section is linear, and this is a triangular variation, we know this triangular variation is constant across B. Therefore, when we integrate in 3D over the area, the centroid of this triangle is the centroid of the, in terms of elevation, the centroid of the compressive block in terms of the area over which the stress is applied. Therefore, we said the resulting force is at 2/3 of x from the neutral axis. Therefore, the R in this case is equal to D minus x divided by 3. This is the arm. Then we talked about the forces. The tensile force was easy because the area of steel is small. In terms of the height, we assume the stress is constant. But for concrete, the stress would vary linearly across the depths. This is the average stress, this is the area. And then we plug them in, we simplified, we arrived at this equation. Has two parts, tensile force and the arm. R is J times D. J is a coefficient multiplied by D gives you the arm, the distance between the tensile and compressive forces. J is simply 1 minus K divided by 3, where K is a constant multiplied by effective depth gives you the compressive depth, which can easily be calculated based on this. All of these are for rectangular sections only. If you have a different section, we need to do it differently. At this time, we are just talking about rectangular sections.
Professor?
Yes.
So when we're talking about under service conditions, when will we use 1/2 of the forces still? Like,
So that goes to, we'll look at an example in a moment. This Fs could be any number that you want. You can say Fs, I want to be 1/2 of Fy. This is the stress in the rebar. You can say I want to limit the stress in rebar to 1/2 of Fy. So if this is 1/2 of Fy, from this you can find how much moment you have. We'll look at an example in a moment.
and then the compression force.
We haven't looked at compressive force yet. We do it now. So now let's look at the compressive part. M service is equal to C times R. C is equal to 1/2 of FC BX times R when the R is D minus X divided by 3. X is equal K times D, therefore is equal to 1/2 of FC B K times D times D minus KD divided by 3. Is equal to 1/2 of FC B K d squared, I factor out d from here, 1 minus k divided by 3. One minus k divided by 3 is j. It's equal to 1/2 of fc j d, like j, let me put kj, k j b d squared. 1/2 of fc, I just rearrange these terms, put kj first, then bd squared. So this is how we relate the stress in concrete to the service moment. 1/2 of fc kj bd squared. If M service is given to you, you use this relationship to find Fc, you use this relationship to find Fs. And you say, this is the result of section analysis. Because you gave me moment, I'll give you the stresses. Alternatively, one could be asked, I want to limit Fs to so much, and I want to limit Fc to another value. What is the maximum moment I can apply? You use this and you use that. Based on either one, you find the corresponding maximum moment. So let's look at one example now. Let's look at the same section that we had. F prime C 4 ksi, Fy 60 ksi, 12 by 18, 3 number 9. What we want to solve is this. We want to have Fc less than equal 1/2 of F prime C. Why do we want to put a limit like this? More specifically, correct? What would happen if we do this? As a result,
To avoid permanent damage.
in compression, correct? To avoid permanent damage in compression, or to minimize permanent damage in compression. And then we also limit Fs to less than half of Fy. Why this limit? What do we control with this limit? Crack size. So this controls concrete in tension. We are putting limit on steel bar to control the crack size. So this would control crack size, this would take care of concrete in compression. This also makes limits the rebars in the linear range. If it's less than Fy or even Fy, it would be linear. So if we have these two, the question is, what is M service? We have calculated K from before. K was 0.4. Therefore, X was 6 inches. We did it last time. If we want to use this relationship for rebars, we need to calculate J. J is 1 minus K divided by 3 is 0.867. Then M service is equal to AS Fs JD, which is equal to 3 times 1. That's the area of the steel. 3 number 9 bars, 3 times 1. Fs, we want to be at most 1/2 of Fy, multiplied by 1/2 of 60. J is 0.867 and D is 18 minus 3. If you multiply these things out, you get 97.5 cubic feet. That means if you limit your moment under service condition to 97.5 cubic feet, of course, maybe I'd better write it in cubic inches first because the units are in cubic inches. So in cubic inches it becomes 1170 cubic inches if you multiply this out, which is equal to 97.5 cubic feet. So if we limit the moment to the section, apply to the section to 1170 cubic inches or 97.5 cubic feet, the stress in the rebar would be 1/2 of Fy, which is one of our objectives. At the same time, we want to make sure that the stress in concrete is also less than 1/2 of F prime C. Therefore, M service is equal to 1/2 of FC JD JK or KJ B D squared is equal to 1/2 of. We want FC to be limited to 1/2 of F prime C. Therefore, I replace FC with 1/2 of 4. K is 0.4. J is 0.867. B is 12. D is 18 minus 3, and we need to square it. If you do this multiplication, you would get 936 cubic inches, which equal to 78 cubic feet. If you limit the moment to 78 cubic feet, the concrete compressive stress will be limited to 1/2 of F prime C. Therefore, if we limit the moment to this value, concrete would be in good shape, the steel would also be in a good shape because it's certainly less than 97.5. Conclusion, M service is equal to 78 cubic feet, which is the minimum of those two numbers. Questions?
The, for the arm length for D, we go with 18 minus 3.
This is not arm length, this is effective depth. Arm length was J times D. Just look at this equation. ASFSJD. J is 0.867, D is 18 minus 3. Why? Because we said unless otherwise mentioned, this is 3 inches. The arm is this, or this. This is the arm. Questions? In the midterm exam, you will have one question M-Crack, one question M-Service. You already know 2 of your midterm exam questions. The way we did the calculation here was based on calculation of force and R, and not based on the calculation of the moment of inertia. This calculation is specific to rectangular sections. More often we use rectangular section, and if that's the case, use of this method is the easiest approach to solve the problem. Alternatively, if your section is not rectangular, which this cannot be used, or you would rather to use the moment of inertia, you can solve this problem using moment of inertia. That's a different method of solving it. This is one method. Now let's talk about the second method. Before I move on to the second method that is based on the moment of inertia, any questions here? Is everything clear? Keep in mind you will need to do this in your homework as well as in the midterm exam. Is everything clear? Now we want to talk about the general section, any shape. Find location of neutral axis. That's the same as before. You find the centroid of the section, and that's the location of the neutral axis. Then you would relate stress to moment through my over I. In order to do this, I should be calculated for the cracked section with respect to its neutral axis. So let's calculate the moment of inertia of that section. I is equal to the moment of inertia of top part, 12 times 6 to the power of 3 divided by 12. That's the moment of inertia with respect to its own centroid, plus 12 times 6 times 3 squared. That's area times distance squared, plus the moment of inertia of rebars with respect to its own centroid. We said we neglect that part, plus area distance squared. 8 times 3 times 15 minus 6 squared. This is the distance between the rebar and the centroid or neutral axis, which is d, which is 15 minus 6. If you do this calculation, you would get moment of inertia equal to 2808 inches to the power of 4. You can see that this moment of inertia is significantly less than the moment of inertia of the uncracked section. Could you look up, tell me what was the moment of inertia of uncracked section? How much was it? So almost twice this. What does that mean? After the section is cracked, the moment of inertia drops significantly, which makes sense because there is no concrete in tension anymore. So in any case, we have this moment of inertia, and then we can use that to calculate. Let me not, I erased it anyway. So when we use that moment of inertia to calculate the stress, we say Fc is equal to M surface times what? What would be Y for concrete? What number should I put here? Number. How much? Six. That's the distance between the centroid and wherever you want to calculate the stress. Here is stress at the very top, divided by 2808, equal to FC is equal to 1/2 of F prime C, is equal to 1/2 of 4. From here, if you calculate M service, you will get same number as before, which is 936 kip inches. And if you use Fs equal M service times what number? Times 15 minus 6. 15 minus 6, which is the distance between the rebars and the neutral axis, divided by 2808 is equal to 1/2 of 60. Now we want to limit it to 1/2 of Fy. From here you find M service is equal to 1170 kip inches, and this is your moment in kip inches. You can convert it obviously to kip feet, which is going to be 78 kip feet. Usually when I give you a problem like this in the exam, I don't tell you what method to use. You can choose your method. The smarter approach would be, depending on the problem, choose the simplest approach. As you do your homework problems, you decide, you develop this understanding as to which method you would rather under what condition. In this problem, which one of the two methods do you think is easier? First one. Why?
Because we already have the formulas for the rectangles.
And you don't need to calculate the moment of inertia. The first one, you just plug in values and you solve it. If your section is rectangular, usually the first method is easier. Can you solve it this way? Sure. The only thing is added is I. If you calculate moment of inertia, then you have an equation here too. The advantage of this method is, if the section is not rectangular, that method is, the first method would not apply.
I'm sorry, that 15 is the height of the...
15 is the effective depth, is the distance between the rebar and the very top.
Okay.
So if we subtract 6 from it, that's the distance to the centroid.
In FC, it's M service times 6 or times. That's a 6.
This is 6 distance from the top to the neutral axis. This is 15 minus 6 is distance from the rebar to the neutral axis. So if no more questions, why don't we just stop here and start at 9:50 again.
You want me to remind you today about scheduling the...
Yes. Let's talk after the class. Yes. Oh yes. I'm glad you are here. So there is one more lecture next Tuesday.
Yeah, next Tuesday.
Thank you.
Yeah, you're welcome. Have a good day. Have a good day. Have a good day. Have a good day. Have
Have a good day. Have a good day. Have a good day.